All right, and so in this additional example here allowed me to show how to use the washer method to find the volume of a solid that is generated by rotating a given region around a given axis. Okay, and before we get started, this video lesson is highly recommended to be viewed or watched after you have seen my video lecture on the general discussion or the general or teaching about the washer method. Okay, or in general the lecture about how to find volume of a solid that is generated by rotating a region around a given axis. Okay, so here we go. Let's turn over to the wording description of the problem here on the computer screen here. All right, so here we go. We are at this problem here where it says we want to find a volume that is formed or created by rotating the region enclosed by, we have a function here, y equals 0.6 minus 0.6 times absolute value of x minus 2, and y equals 0, and then about the y-axis. Okay, so that's the complete description of our problem right here. And now allow me to use my graphing calculator with Desmos.com right here to one by one show the graphs. So we need to show the graphs of these two equations here. So we have two graphs. One of them is given by y equals 0.6 minus 0.6 times absolute value of x minus 2. And the other graph is the line y equals 0, which is a different name of the, which is a mathematical name of the of the x-axis. Okay, and so let's find out what that region is. And the region is enclosed by these two graphs here, by these two curves. They could be curved, they could be straight line. Right? So let's find out. So the region is enclosed by these two lines right here, these two graphs. All right, so now I'm going to switch over to Desmos to see what those graphs will be create the region for us, what the region looks like. All right, so here in our empty graphing space right here, the graphs of the two equations are as following. And so the graph for 0.6 minus 0.6 times absolute value of x minus 2 is this nice V curve right here, but pointing down. Okay, this nice V curve pointing down, and then this is in this other red line right here is placed right on the x-axis. This is the line of y equals 0. So the region that is enclosed must be this region inside of the two curves right here. Okay, and so that's all there is. So now I am going to make the shading of the enclosed region, and I'm going to restrict the graph so that it only shows the enclosed region. So now the enclosed region has just now been shaded, and so now I'm going to be restricting the graph. I'm going to put out all of the other extra details just now so that we will only need to focus on the region to be rotated. Okay, so here's there is that enclosed region. So this broken, so it forms, the region here forms like an isosceles triangle over here that's standing straight up. Okay, and so now in 3D view over here, where we're gonna start seeing the rotation, because the problem is telling us to rotate that region. So from this region here that I highlighted, we want to be rotating that about the y-axis. All right, so that's how the rotation happens. So the problem indicated that for us. So all we do is just we try to understand, we try to imagination. So I put on the graph to help anyone's imagination about how the picture is going to look like. So in that way, now in 3D view over here, this same region in 3D view. All right, so that is the x-axis is here, the y-axis is here, which we will be rotating this blue region around the y-axis. And again, just like how I explained in the video lecture, the general discussion video lecture, like that, then the orientation of our rotation should not matter. So here I'm rotating on the y-axis. Here I'm rotating counterclockwise. Okay, so now let's observe the rotation. So here's how the rotation happens. All right, so now as I'm rotating it, that's the picture that we're creating. So right at about halfway through the rotation, then allow me to take a quick pause here. So the real solid part is here where it follows along. So the real solid part, imagine that we have to go inside of that space right here, so that triangle being rotated around, and it create kind of like, and so, but so it's, I'm not even sure what that shape is anymore, what that solid is called anymore, but the empty space is out here, and the solid space where we are calculating the volume is the part that's going in here. Okay, so imagine if there's like a bug that's going through this hole right here, then that's the volume, the space that we're calculating the amount, but outside here that's just empty space. Okay, and now completing out the rotation, and that's the kind of picture we have right here. All right, and so now I'm gonna also adjust the view of the axis here, of the 3D axis, so that viewers can have a little bit of a better understanding of the picture over here. All right, so rotating the axis is on the floor is not anything doing much for us, but that's it. Now, so now when we're turning that into a slightly different view right here, okay, then okay, so from original shape right here, now we're looking at all right, so now it's better revealed the form of the shape. So I mean, honestly speaking, it looks a little bit like a dog food bowl right here, but it's empty. The empty part is here, and then we're not calculating the part inside here. We're calculating that part out. That part being around here. Okay, all right, and so there's another picture of that in a slightly different angle right there. All right, so now I'm gonna switch over to my board to do some actual sketching, so that we can make some planning about the problem right here to tackle it down. Okay, so now on my board, again the picture we saw there. Okay, we're gonna be rotating it around the y-axis, and allow me here to be a little bit upscale right there. So what I have here is what I saw there was a triangle. So we have a triangle, okay, an isosceles triangle with the two equal sides here, okay, and the base of that triangle here. And so the shading, this is how the shading happens, okay, so that's the shading right here. And so now as so put in your imagination, if we're rotating that around the y-axis, this given area right here, this given region, and there's our x-axis, our y-axis is here. And so right now, in the way how the equation gave us, then the two sides of this isosceles triangle here comes out from one curve, one equation. So I only need to make label on one right here. So this whole broken line right here is that line y equals 0.6 minus 0.6, and I noticed I wrote it a little too close to the right hand side, so I'm gonna change that to here. So y equals 0.6 minus 0.6 times absolute value of x minus 2. Okay, so that's this line right here, this broken line, two pieces of a line. Okay, and then the bottom here, the bottom boundary here is found by the line y equals 0. Okay, so we have only really two graphs that's determined, that enclose our region right here. But now as we're getting into the further stage of our planning right here, then just like how I explained hopefully thoroughly enough in the general discussion lecture, then in this way right here, now the y-axis is our rotation axis. So that means I am going to, now through my region right here, from the region right here, I have to draw stripes that are, I have to place the stripes that are perpendicular to the rotation axis, and in this case the y-axis. Okay, and then we placing our eyes, and again we have to imagine that our eyes here are being placed to look down. So there's the eyes right here, and the eye is looking down, so the y-axis is coming up this way, and we're looking down on that, and as we're rotating, each stripe is going to create for us a disc or a washer depending on how it looks. Okay, and so now just like that, again in connection with what I was explaining in the video lecture about the general discussion on the washer method, due to the nature of this kind of figure right here, due to the nature of this kind of region, once we're rotating it and once we place the stripe right here, then so some part of the stripe is inside the region. some part of the stripe is inside the region, and the way how it is, the stripe must cross through, see, the stripe must cross through the region boundary at least one boundary right here. Okay, so there has to be a point where the stripe cross through the regions to make its way to the rotation axis, and once crossing through that the region boundary right here, then there's going to be a part of the stripe being completely outside of the region right here, and that's why I'm putting it dotted here. All right, and so now, and then in that way, now another point to make it consistent with the explanation I deliver in the general discussion lecture. But so in the way how it is, so if we look straight on our stripe right here, then there has to be one point or one part of the boundary being closer to the rotation axis, and there's another part of the boundary of the region here being further away from the rotation axis right here. Okay, and so we have a point that's closer to the rotation axis, and we have another point that's further away from the rotation axis. And so, and one generality we can see here is that the point that is closer to the rotation axis, that point is the point where the stripe here crosses through the boundary, whereas the point that's further away from the rotation axis, is that point where the stripe stops at the end of the region right there, at that boundary. So the stripe stops at that boundary, causing that point to be the point that's further away from the rotation axis. Okay, and so in that way, of course, so now naturally enough, and as a consequence, now once we are rotating this, or this figure right here, this region once rotated, it's going to create for us now the closer points from the center of rotation, from the axis of rotation out to the closer points. That piece of stripe right there, even though dotted, but once rotated, it will create an inner circle. Okay, and then from the rotation center out to, or from the rotation axis out to the further point, that amount of length right there, that stripe, that long lengthy stripe, once rotated, it will create for us the outer circle right there, or an outer radius right there. Okay, and that's the reason why we're seeing in front of us, in front of our eyes right here, what we're seeing here is a washer. Okay, so as another picture, I'm going to put that in the little space that belongs to the other board. But I don't think I need to switch the board space, the board angle here. But see, in front of our eyes now, what we have there is the picture of a washer. Okay, the rotation axis comes right through here, and this is the solid area part that we can actually calculate. And then so now there's always, in the way how the washer is, see, from the rotation axis here, then as we're rotating the stripe, the longest stripe right here, the stripe that connects to the outer boundary right here, creates the larger radius, and the stripe that goes to the closer points, okay, the point that's closer to the rotation axis, it creates the shorter radius, the smaller radius, the radius of the smaller circle. So there's an inner circle being smaller, there's an outer circle being larger, and these two circles are once again concentric circles. Okay, and so now in that way we have enough information now. And then of course, in a side view right here, I mean looking straight into the graph in this way right here, if we are placing our eyes to look straight in here, then each washer there is looking as like this picture that's describing. Okay, and so now I'm seeing that we have a thickness. Each washer has a thickness, and I'm trying to describe the thickness here. The thickness, okay, the vertical amount here would be the thickness, because our washer, each of our washers is being placed sideways. It's just exactly the way, I mean, it's just naturally the way it is once we're rotating this region around the y-axis. The y-axis is chosen. The problem chose that for us, and so now that's what we need to put into our imagination, in our visualization right there. Okay. All right, and so the solid area part is here. And so now, just like the many times that I have explained throughout my in my general video lecture about this method right here. Then to obtain this volume created by rotating, to obtain this volume, to calculate this volume obtained created by rotating this region right here, then the only fundamental we're doing here is we're accumulating little volumes. We're accumulating all the little volumes. So we're accumulating those washer volumes, the volumes out of those washers. So, but in the end, each washer here, if we're looking straight down on that, it's a cross surface. What we have here is a cross section. Okay, cross section. And so now what I'm doing here to each washer, on each washer, what I'm doing here is I'm gonna find a cross section. I'm gonna find a cross section area. That's the first thing. And then I'm gonna multiply the cross section area with the thickness. All right. So thickness multiplied with cross section area. That's how it gives me the volume of any one particular washer right here, no matter how thin that washer is. And I keep saying this many times throughout my general video lecture, but the washer like this has the width right here, or the thickness here, is supposedly the infinitesimally thin thickness. Even if I'm just drawing a washer like this, I'm not lying at all that it has a thickness. It's just the thickness is done by just how thin my pencil stroke is, my marker stroke is. Okay, so every washer here has a thickness, and that thickness is being measured along the vertical axis, and we will get even further into that. All right, and then once we come up with a generalization for the volume on each washer, then we're going to be accumulating all of the little volumes, all of the washer volumes from a start to an end. And this is the only one fundamental that throughout all of my examples and throughout all of my lectures regarding finding volume of these rotating the solids right here, of these solids that created by rotating a region, then this is the only fundamental that I've always been relying to. Okay, and so in that way, now let's look for, according to my suggestion, according to my recommendation, let's try to realize and recognize the thickness on each of our washer here. Okay, so in a way, how we place our washer right now, any of our washers, then it looks to me that, you see, this vertical, the thickness has to be the vertical dimension in the way how we place the washer here. So now it's easy to recognize that for our thickness on each washer right here, in the way it's the infinitesimally small change in y value, and so we call that it's the dy differential. So thickness now is all sudden realized to be the dy differential. And again, I repeat, it's simply because in the way how we're currently placing any of our the washer right here, then in that way the thickness is being measured along the vertical axis here, the y-axis. And that means the thickness here is measured as the infinitesimally small change in y coordinates, in y values. And that's why we arrived at this dy differential over here. Okay, so that's the thickness. And now we are ready to start filling in. We directly fill in the information that we have realized into this general fundamental formula for accumulation. Okay, so in this setup right here, yes, it's accumulation from some start to end. We haven't found out where the start of the solid and where the end of that accumulation yet. We have not found out a formula that determines the cross-section area, but we will get to that. But now we know for sure one thing. We know for sure the thickness that's just now recognized through the picture, it has to be a dy. So every cross-section area must be multiplied with a thickness being a dy. That's how it's done. That's how it's realized and being placed appropriately into the formula. Okay, and so now at the steps right here, and the reason I say that this is my own recommendation, because for me it helps me in a sense that once I realize about my thickness right here, it becomes my d expression in the entire integral problem, and this d expression is indicated in terms of y. So that tells me in the next step that I am responsible to find this to come up with this cross-section area as a function with the main variable in terms of y. Okay, it's making things consistent with how I started the teaching about an integral, either a definite integral or an indefinite integral, that the main functions, the main variable has to be consistent with the d expression here. Okay, and so now once we have all that pieces of details in mind right here, let's now start looking into coming up for ourselves the cross section. Okay. So for cross section, let's see what we can do. Cross section area. All right. So how would that look like? So allow me to swing it over to the other board because I have that picture here. So now as we're looking straight into that cross section, it appears to be a washer as I have been saying it. And of course, this kind of example is where we're accumulating washer volumes, and that's why it's called the washer method right here. But in the end, this is the area where I'm shading here is the area that we need to calculating. But that area with simple geometry understanding, then we can just see that it's just the larger circle, the area of the larger circle minus the area of the smaller circle. That gives us the area between, and we're excluding out that empty space here. All right, so in that region, in that reasoning, in that way of reasoning, then the area of the larger circle is pi big R square. That's the area of the larger circle. Okay, pi big R square. And then the area of the smaller circle is pi times little r square, right there. Okay, and we're subtracting that out. So larger circle, area of the larger circle minus the area of the little circle, that gives us this. Okay, but now it is our responsibility. So allow me to recreate the picture here. But here in this problem, there's another challenge that's waiting for us here. So every example that I deliver has its own specialty and has its own challenge a little bit, being on top of those examples that I deliver as the basic example in the main lecture itself. But here, the region itself, really, I highlighted this earlier in the other board. This is really one curve. It's the curve of the absolute value function. It's the curve of the absolute value function. But now for the need of our problem here, think about each stripe. Think about each stripe as we going through the region right here. Okay, so here's the shaded region. So each stripe, again, allow me to make the dot right here. So the dotted part is the shorter radius. So the dotted part is the dotted radius. Okay, the shorter radius is the dotted stripe right there. Once rotated, that becomes a shorter radius. Now, the longer one is the one that has dotted and solid in it. Okay, dotted stripe and solid stripe in it, and that's why for the longer stripe right here, so in any way, each stripe right here, the shorter stripe, the shorter radius, where it comes from the rotation center out to the closer curve right here, that short curve right here, even though it's just only one piece of the, recall I just said earlier, this whole broken up line right here is y equals 0.6 minus 0.6 absolute value of x minus 2. That's one function. But sadly, it must be broken up into two pieces of boundaries right there. Two pieces of boundary. So in that way, and you can now notice clearly that in the way how the picture looks, then right around that breaking up point right here, then this piece is closer. This piece is where is closer to the rotation axis, and this piece here of the boundary, this other boundary here is further. So this is closer on the left hand side, and this is further. Okay, and now here's how the stripe from the rotation center out to the closer piece right here, that must be expressed. Now we have to come up with our way to find out what that curve is as a function of okay, we need to express that as a function of y, because see, at different y value we reach a different height right here. So at this value right here we have a shorter height, and then when we have a shorter length right here that's coming out to hit the region, and then as a different y value, we have a different height right there. We have a different length that reach out to the two boundaries right there. And so now it's our responsibility, even though the two broken lines here came out from one graph, but now it is our responsibility, and that takes a little bit of a challenge. That's why I brought up this example right here. So we need to find out a way to break the two separate little curves here as a functions. Okay, that one here on the left and that one here. Okay, the two curves there as two functions in terms of y right there. There's the inner radius and there's the outer radius is here. The inner radius and the outer radius. Okay, and so now let me clear out a lot of writings here so that I can start doing some algebra. And again, I have all my legitimate reason to keep reminding my student and yelling out loud in front of anyone watching this lesson right here. You gotta get your algebra going. Okay, the more we going further into calculus, the more we realize the importance of algebra. We cannot get away from algebra. We cannot get away without algebra. Okay, so now here's how I'm finding it. Now let's give a closer look at this absolute value expression right here. Y equals 0.6 minus 0.6 times absolute value of x minus 2 right here. So in that way, we know that that's why it gives us the graph being this V curve right here and have a sharp corner right there. Okay? And then I'm going to use my red marker to indicate it's just the property of absolute value function that anyone arriving at this video lesson, supposedly you are at a calculus level, you should know from your algebra understanding that the V shape right here, that called traditionally the vertex of that, the V shape right there is happening right at, okay, that vertex is happening right at x equals 2 because of that. Okay, and so allow me not to go too far back into the ultra basic stuff of algebra right there, but that x minus 2 inside of our absolute value tells us that the vertex of that V shape right there, and it's pointing down because there's a minus in front of the absolute value. Okay, but in the end, the vertex here is right at that line x equals 2, the vertical line x equals 2. And so that means, and so right from that, once I place down that red vertical x equals 2 line right there, then we immediately notice the behavior changes. When x is less than 2, then we having the line is even though it's just a short segment right here, but it's a pointing up slope right here. And then in this piece of the line right here, it's a pointing down slope right there. It's a negative slope here, and it's a positive slope there. Okay, and so now here's how I'm seeing it. So it's all starting out with one function, y equals 0.6 minus 0.6 times absolute value of x. But now algebraically, you must have your algebra, you must reveal your algebra here in order for me to continue with this. So at any point, if you feel unsure about what I'm about to deliver here, go ahead and pause the video and reveal your algebra understanding. Okay, and then we can wrap it up after. You can go ahead and proceed afterwards. But so here, assuming you already have some background in algebra, then this absolute value right here means the same function y, but will equal to two cases. The same function y will equal to 0.6 minus 0.6 again, but times x minus 2 without absolute value. And without the absolute value, the expression here looks just exactly like the part inside right there. But it's only like this, x minus 2. It's only happening when x is greater than or equal to 2. That means the absolute value curve right here will equal to this function without the absolute value for x greater than 2, which is this piece right here. And so think further, and it's all, like I said, if any of you unsure about this, make sure you review your algebra. Okay. And then the same absolute value function. Now, if we try to take away absolute value to turn our function into something ordinary, then it will be 0.6 minus, it's that 0.6 again, but now it becomes 2 minus x. 2 minus x for x being less than 2. Okay, so the last, the only little bit of reminder I need to point out for anyone, simply because you must notice from algebra, absolute value of x will equal to x itself. Okay, if the expression here is greater than or equal 0, and then it will be equal to the opposite of x. I'm saying the opposite of x. If x is less than 0, like that. That's the property that we got to remind ourselves from algebra, and that famous property of absolute value. And this is what it is here. Now, instead of 1x, it's just an expression inside the absolute value, so the expression remains exactly the same. Just like that, the expression remains exactly the same when our part inside of the absolute value here is greater than 0, and greater than 0 in this case means x is greater than or equal to 2. Okay, and then the other way around. This means the opposite of x minus 2. This really means minus x minus 2. Okay, and that's what just making it like that famous property. And this is happening when x is less than, when x minus 2 is less than 0, but that essentially means x is less than 2. Okay, and so now, once we've had all that, what's useful about this? What's useful about what I'm doing here? So that means now I'm going to have to allow me to do this a little bit of a dirty solution, because I don't have enough board space right here, so I have to erase things and then kind of rewrite it and to make it look a little more neat here, to look a little more recognizable. Okay, but you see now we can just simply, for the top equation right here, when y, for that first case, when x is greater than or equal to 2, we can just simply algebraically distribute out that 0.6 right there. So really our y will equals 0.6 minus 0.6x, but plus 1.2. That's what it is. But 1.2 is like term with 0.6, so 1.2 plus 0.6 is the same as 1.8. So really, my expression here is saying that y would equals minus 0.6x, okay, plus 1.8 when x is greater than or equal to 2. That's how I'm rewriting our expression there, when x is greater than or equal to 2. Okay, so that we knock down one case right there. And then for the other case, again, very similar work. I am going to distribute out that negative 0.6 to each term right here. That gives me 0.6 as scratch work right here. Scratch work 0.6 minus 1.2. Okay, and then minus 0.6 times negative x times minus x gives me a plus 0.6x. That happens when x is less than 2. So algebraically we can combine like terms with these two constant terms here. Okay, and that's leaving it. So here we're looking at y will equal, on another case, a positive 0.6x. Okay, minus 0.6 when x falls below 2. All right, so ladies and gentlemen, what I have just done now, and we're just about halfway of deriving. Our goal again is to re-express that piece of the curve and the other piece of the boundary in terms of y. But so far I'm still beating around the bush with y as a function of x so far. But we're a little bit over halfway now. We're a little bit over halfway. The biggest door we've been through. We successfully broke our curve into two separate pieces already. We broke our one boundary here, our broken up boundary. Supposedly one boundary, but we broke it down into two pieces. So this one here is the right piece. See, this one here, that one here is the right piece. So now I can start putting it into my picture over here. The further curve, the curve that's further away, the boundary here that's further away from the rotation axis, this part here is y equals minus 0.6x plus 1.8. See, and checking for consistency, because that piece of curve here stays to the right hand side of x equals 2, or because x is greater than or equal to. Okay, and then with this closer curve right here, now instead of saying that closer, we know it's closer, of course, that's because the picture is telling us with our eyes right here. But now with this closer curve, mathematically or algebraically, that's the curve y equals positive 0.6x minus 0.6. That's the curve right here. See, positive slope, positive slope. Okay, and then it should be having y-intercept at some value being negative 0.6 down here. And that's the whole idea. So I broke that down. I broke this one boundary, this broken up boundary into two separate pieces. Okay, and so now once we've had that done, now I also need to erase this stuff. So much work, but now I have to keep erasing it. All right, so now from the further curve right here, we need to express that in terms of y, re-express that in terms of y. So y equals minus 0.6 x plus 1.8. Essentially, this is the same as y equals negative 3/5 x. In fraction, I'm a little more comfortable with fraction. Plus, and this 1.8 right here is the same as a 9 over 5. Okay, so that means now we can solve for x in terms of y right here. I am going to multiply both sides by 5, giving me 5y equals minus 3x plus 9. And I'm subtracting 9 to the other side, so that leaves me 5y minus 9. Okay, equals negative 3x. And now the last step here is to divide both sides here by negative 3 like that. That leaves me x equals minus 5/3 y. Okay, and then plus 3. Okay, minus 5/3 minus 5/3 y plus 3 equals x. So this is the further curve. This further curve right here has an alternative writing. All right, so this further curve has an alternative writing being x equals, okay, same curve, but x equals minus 5/3 y plus 3. All right, and so now I'm working on my way to re-express the other curve. And again, I have to erase the board to make space for my next work right here. Okay, so this other curve, y equals positive 0.6x minus 0.6. Okay, and so now what I'm seeing here, that is the same as y equals positive 3/5. I mean, yes, 3/5 minus 3/5. Okay, and so now solving this for x, I'm multiplying both sides by 5, giving me a 5y equals 3x minus 3. And then adding that 3 over and then dividing both sides by 3, I'm ending up with x equals, okay, so now it's going to be a positive 5/3 y, okay, and then plus 1. Okay, so now allow me to start going a little bit, picking up pace on the algebra over here. But so this curve, where I call that, it's the curve closer, the closer curve, the curve that's the boundary that's closer to the rotation axis. So that curve now we can also express that curve as x equals 5/3 y plus 1. Okay, 5/3 y plus 1. And that's how I express this closer curve. So any stripe being placed this way, when it hits the closer curve, that distance there, that radius there is regulated by x equals, it's found by as a function of y now. So 5/3 y plus 1. Whereas the longer radius, now the longer radius is x equals minus 5/3 y plus 3. And so now once we've had the two boundaries, they are successfully written in terms of y as a function, then now I'm ready to make my way right here. So back to this formula, this ultimate fundamental. Pi times a big radius square. Big radius is here. So any length there, at any y value, the length of that radius is determined by this function in terms of y. So now I'm looking at pi, okay, pi times minus 5/3 y plus 3 all squared. That's, ladies and gentlemen, the area of my larger circle, written completely, expressed completely in terms of the y variable. And then for the next one, minus the area of the smaller circle. So the radius of the smaller circle is regulated. Any distance here from the rotation axis out to the closer curve is written as a function of y. So 5/3 y plus 1. So right here, 5/3 y plus 1, positive 5/3 y plus 1. But now I need to square that radius. So now I have derived for myself a general formula for the cross-section area. This is the cross-section area. Okay, so now I'm ready for taking that into my other board and fill that in right here. So cross-section area, now we concluded that it has to be now as a, now we have a common factor, so I'm going to pull it out, and then we're looking at minus 5/3 y, 5/3 y plus 3 all square, and then minus, and then there's that positive 5/3 y plus 1 all square. And this is our formula in terms of y, our function in terms of y representing the cross-section area or the area of the cross-section. And so now I'm ready for filling that in. So now into my actual function. Okay. dy is here. I can write pi here. And then so now I'm going to copy and paste that exact expression here, minus 5/3 y plus 3 all square, and I'm going to subtract, and now positive 5/3 y plus 1 all square, and then all of that there as one function multiply with thickness dy. And so now we're almost complete with our integral setup for this. So this is each volume, the volume for each washer already, but we need to know where we start the accumulation and where we end our accumulation. We need to recognize the starting and the ending of our accumulation. Okay, so in that way, here's how I'm seeing it. Okay, so just like that, so now things are starting to get easier now through that stage right here. We're rotating around the y-axis. So throughout my explanations, I offered many times in the general video lectures, and you might have seen that in some other video lessons as well on the additional examples. Then anytime we're rotating around the y-axis, a region rotated around the y-axis, then the accumulation happens from bottom up. Start at the bottom and ending at the top. So from bottom up, okay, so the accumulation goes start at the bottom and ending the accumulation at the top. All right, so now easily you can see that, and allow me to get on the other picture that's a little cleaner. So in this picture right here, in this picture, or actually it's better that I can just draw a brand new picture here. Okay, so with that, this is allow me to be a little off scale. Okay, the line x equals 2 is here. X equals 2 is this vertical line, but we're going in terms of y value, in terms of y variable from bottom up. So bottom makes sense to be this line right here, y equals 0. That's bottom. But how high does this reach? Now, algebraically, we need to solve the two curves here, set them equal to each other. And we need to solve the two curves in terms of y and then solve them, letting them equal to each other for solving for y value to find the top value right there. Okay, to find the top ending. But here, I mean, that's not the only way. I mean, sometimes if there's, and it's still the algebra again, sometimes there's a faster solution, we can just go with that. But you see it. Now we utilize our understanding of the absolute value curve. So this argument I'm doing here is only specialized for this for our specific function here being the absolute value. But the absolute value function like this, especially when anytime it's pointing down like that, it will hit to the peak point, the highest point, to the high point when we write at x equals 2, when we write at that center of symmetry right there. On the picture. Now it's not the center of symmetry through the y-axis, but it has a center of symmetry right through that region right there. Okay, so x equals 2 is that middle line right through the region. And so now I'm going to just substitute, because our function originally given as a 0.6 minus 0.6 times x minus 2 in absolute value. So now just simply substitute x equals 2 into this expression. That gives me a 0 out on this term right here, and so this maximum y value has to be y equals 0.6. All right, and so now, see, we have to substitute. So y at x equals 2, substituting in, that gives me a 0.6 minus 0.6 times 2 minus 2. That's what I'm saying right there. And we don't have to solve the equation, but we're substituting directly that x equals 2 value, because it happens right on that line of symmetry where the vertex is at as well. Okay, and substituting that, we get that height, the y value of the height. So that y value comes out to be a positive 0.6. Okay, so y comes comes out to be 0.6. But this vertical height right here is our ending of the accumulation. All right, so now concluding with our integral setup right here. It goes from the start of the accumulation, goes from 0, from bottom, to 0.6. Okay, and that completes, ladies and gentlemen, that completes our integral setup for the volume, to calculate the volume of this solid once we're rotating that region around the y-axis. Okay, so now I'm going to put this in a circle, this in a box, even though it's not our final answer. It's just to emphasize that we are at that stage now where we're done with completing our integral, and once we've had that integral completed, then we can start finding the answer by using the fundamental theorem of calculus. So again, needless to say, we have to know the fundamental theorem of calculus in order to get things work on this problem right here, in order to get things work. Okay, so now I am going to erase the board on my other board, and now we are ready for solving it. So the integral currently that we came up for ourselves here is an integral accumulation from 0 to pi, to 0.6. Okay, and then we have pi, and then the minus 5/3 y plus 3 all squared plus positive 5/3 y plus 1 all squared with a dy. And so now to make it easier, I am going to spend some time, at the same time I'm pulling out that common factor in front as a coefficient. Okay, so there's pi in front, and then the integral remains the same. I haven't done the integral yet. Now I'm going to go ahead and spend some time foiling out the two terms right here. So that gives me 25 over 9y squared for the first term, minus 10y plus 9. And then I'm going to add, and actually I'm doing it incorrectly here. It's supposed to be minus. Okay. All right. So my apologies for that little incorrect sign right there. So minus. Now I'm going to have another 25 ninths, positive 25 9 y squared. I'm going to add with 10/3 y, and I'm adding 1. Okay. And I'm going to have to combine like terms and all that, but this is dy right there. Okay, and so I'm going to go ahead and combine like terms. So pi here, and taking out the parentheses and combine like terms. 0 to 0.6 right here, that gives me 25 9y squared minus 10y plus 9. I'm subtracting the 25 over 9y squared. Okay, and then I'm subtracting 10/3 y, and I'm subtracting 1. Okay, and then with a dy. And so now my expression here is cancelled, and then the two terms here combine, and that's combined. So we're looking at the final expression here before we're ready for real action, for the fundamental theorem of calculus. So this is minus 40 over 3 y plus 8. Okay, and this is going to be a dy. All right, so now fundamental theorem of calculus tells us to first find the antiderivative. So now it's going to be pi times minus 20 over 3 y squared plus 8y. Okay, and then we're evaluating this from 0 to 0.6 like that. All right. And now allow me to erase the steps I've had above right here so that I can continue working out my fundamental theorem of calculus. And then at some point I will swing by to my computer station at the desk to just get the final calculated value. Okay. All right, so now I'm going to put a line through right here because here is a continuation of that work. So now fundamental theorem of calculus. So I hope I said this earlier, but now I can say that again. But make sure you view this, anyone seeing this video lesson here. At this point, if you're not sure what the fundamental theorem of calculus is, you can pause this video and find my video when I was giving a lecture about the fundamental theorem of calculus. And that will help you understand the work I'm doing here much more consistently right here. Okay, so now with the fundamental theorem of calculus, I am going to substitute the upper limits of my integral. So now it's going to become, so pi right there, that's a common factor, I'm minus 20 over 3 times 0.6 all square, okay, plus 8 times 0.6. I'm substituting that in, okay, and then with all that there, I'm going to subtract again pi, but times now again I notice the bottom limits here, once substituted into the entire antiderivative here, it's all just a zero out because each term here has a multiply with a power of y right there. So now it's all just a zero out right there. And so now it's just a matter of finishing this calculation. I am going to step over to my calculator, calculator at the computer station right there to get the final calculated value for this. All right, so my calculations show 12 pi over 5, okay? And that is my final answer. And this is the volume of this solid. The volume of this solid generated by rotating the enclosed area here around the y-axis. Okay, and so again, let me mention the checkpoints for consistency right here. We wanted to find the volume as our goal of the problem right here. And so the volume here, anytime we apply integral into finding a volume, the answer needs to be a positive quantity, not even zero, because it makes no fun to have a volume ended up being zero. So, but if your volume turns out negative, you gotta definitely go back and check your work there at some point. Okay, so here we have a positive volume. Okay, but then further on top of that, if anyone wonder about whether you have made, if you were doing it on your own right there, if you wonder if you have arrived, even though positive answer, but was it correctly done with all the arithmetic steps right there, then make sure you double check or triple check with your arithmetic steps, because that's where you're on your own responsibility. And so forgive me in case I made any arithmetic errors here as well. But in general, even if having some minor arithmetic errors here that lead to slightly incorrect the positive answer here, but it should not alter at all the overall structure of our problem here in this example. Okay, and so now before I'm closing down this particular example, allow me to introduce one thing. That this example is special in a sense that, you see, the curve here itself, the boundary, supposedly there are only two boundaries, 1 and 2, because this broken boundary here came out from one function. But really, in our case, we need here and be prepared. I brought up this example so that you can also be prepared that to be more creative later on, that there are times out there where only one curve, but you are in a situation where you have to break that one curve here into multiple curves here, depending on the rotation axis right there where you're at. So this one curve, if we're rotating that around the x-axis, maybe we can use that as one curve. But now, since we're rotating around the y-axis and realizing that we have a washer right there on each cross-section, then we have to break that curve. And so I brought it in so that you can be ready and be prepared that there will be times that you're working with a problem where you need to break one curve, but we need to break it into two separate functions, depending on that's consistent with our orientation of the rotation right there. Okay, so here one curve from y equals 0.6 minus 0.6 in times absolute value of x minus 2, but now we broke it down into two separate curves. One of them is that the minus 5/3 y plus 3, and then the other one is positive 5/3 y plus 1. The skill to turn the problem into an expression in terms of y variable from x in terms of y or from y in terms of x, it all depends on the problem here and there, but that skill is just the algebra. Okay. But here, that generality about the problem here is that I want to put into your awareness that there will be times where you're working with a problem rotating an area around an axis, and in your problem there it makes you to go through it. You have to go through that step where you must break your curve, your one graph, into two separate boundaries so that we can calculate that differently. Okay,